Good afternoon, everybody. Anthony Bustamante over here. I'm going to present the paper Advantages of Machine Learning Networking Monitoring Systems to Size Network Appliances and Identify Incongruences in Data Networks. The authors, Anthony Bustamante, Skarsha Gimmer, Betsengavi, Arpit Pokarel, and Victor Erekponor. The table of contents. First of all, I will talk about the objective and introduction of this paper, the design of the experiment, and then topology use, the analysis of the results, conclusions, and references. The objective. Um, the objective of this paper is to present two advantages that machine learning has over um, data networks. The first advantage that we've identified is for sizing purposes. And by sizing, I mean uh, to predict the amount of resources that a company has to have to hold or to support a quantity of traffic or users. Also, the other advantage that we've identified is for predicting future behaviors, and this has a focus more related to cybersecurity that I will go through in a moment. Introduction. Well, why this is important? First of all, because data network is a common thing and an important and I would say essential part in every company, in not just in companies but in our lives as well as users. We to connect the internet or to transfer some archives files, we use the network, the internet in this case, which is the most renowned maybe network. And to do so, we have to use those networks to communicate with each other. And in this case, there are some tools that we use in this field to collect traffic or to collect data from those networks. In this case, our approach is on monitoring tools like NACS, which is a tool that we use to collect that traffic and act based on that. So far, we are only using that data for static purposes, for example, alert or maybe um, to make some informs, things like that. However, by implementing or by adding machine learning models in those platforms, we could do more things. The first thing is for sizing purposes and maybe also for security purposes. Um, However, in this paper, unless we've been using um, a monitoring platform like Nagios to collect that data and to present the results about sizing and also predicting behaviors. Um, Second, the design of the experiment and topology. Um, First of all, the data set has been collected from a real environment by using protocols like SMMP and NetFlow and stored um, in a monitoring server for 3.5 months. This data has been used for training and also to compare the predictions made by the models afterward with the actual values. The monitoring server used is a general platform which could be used in almost any scenario that involves network devices. Also, the preprocessing of the data and design of the models was made using TensorFlow and Skylab libraries. Companies using experiment we use servers and terminals, firewalls, proxy servers, and Agile software, and protocols like SNMP and NetFlow protocol. Values evaluated and compared with the machine learning algorithms. Um, our focus has been mainly on values like bandwidth consumption, memory consumption, and CPU. In order to understand the paper, every person should keep in mind and should understand this topology. And in order also to reproduce these results, it's crucial to understand this topology. And the topology and every every interface, every uh, word that we've wrote, we've writing here. And since in every chapter of the paper we are usually referring this topology. Another thing also to keep in mind is the flow chart that we use, and it begins since the recollection of data by our Nagios server, the the start of the data, the preprocessing part or the preprocess of that data, maybe also the application of some techniques like dimensional reduction, the training of the models, and also the comparison between the machine learning predictions and the real data. And depending on that, we can know if those results are good enough for our purposes, or we can maybe re- reproduce or try different models, different techniques. Um, we use different models, different algorithms for this experiment. Uh, Here you can see some of the models that we use. In total, we use 13 models. And something to keep in mind is that all these models are really popular in the machine learning community. Therefore, if somebody wants to reproduce or results, it's easy to do so, since probably you will not have problems to get information about these models, about these algorithms, and practically everybody could do this. Analysis of the results uh, for sizing of components. Um, Sizing of components means that you can have some devices in your network, and maybe you can um, probably in a next month get more users, get more workers, and you will have to increase probably the components of your devices, or because if you don't do that, probably you can get some malfunctions in your network. Therefore, that's why we use machine learning for predicting or for sizing new resources, or to know um, how much bandwidth or CPU or memory we will need in order to comply with the new requirements that we will have. For those purposes, uh, we divided our dependent variables and or independent variables. For both them, and this is for training purposes, we had to regulate traffic for 3.5 months. For the independent variables for the proxy server, we use this table. Something to keep in mind is the timestamp, which is just another way to represent time. We also use the connected clients, active clients, and idle clients, but this is up to you. Every person or a person could use different independent variables to know a dependent variable. The independent variable for the firewall or for sizing the firewall uh, was this. We use timestamp, but in this case we use traffic instead of the connected clients. For the dependent variables, um, you can see that again the timestamp value is something common, but the the values that we wanted to size were CPU, memory, and traffic, downloaded and uploaded traffic. Um, um, and for the firewall, we use this range. Again, we wanted to know the amount of CPU and memory that we will need back then. Um, this is the relationship used for the proxy server, for the firewall, and also the relationship of the samples. For the proxy server, in order to know the dependent variable, we use, of course, or we train our machine learning model mm, based on the timestamp, um, the connected clients, active clients, and error clients. The relationship used for the firewall was quite similar. Just keeping in mind that for firewall, we have more independent variables, which is every single interface of that firewall. And this is another thing to keep in mind, which is the relationship between the samples taken from or for training purposes. In this case, using this 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 amount of units, it's more than enough. However, due to some limitations, we had also to use um, this arrange. Um, However, with this amount of units is enough. Uh, the results for the proxy server, the results are exemplified here by using R square. Um, R square coefficient. This is a common technique in machine learning to measure regression models. By the way, this is something to keep in mind, that all this paper is based on regression models, and therefore R square is one of the techniques that we use to know if our models were working fine or not. Another technique or another way to measure this was by plotting our results. Um, Here in this table, you can see all the results of, um, or sorry, for sizing purposes, of every single algorithm. You can see that the results are good enough. The results here indicates, or the way to interpret these results is, um, the the closer the value is to one, the better the results are. Therefore, you can see here that some of the results were quite good. However, some others were not that good. Um, Even though these values were not that good in the next step that we did, we could realize that we don't have to focus completely on the R square values, but also plotting the results. And by plotting the results, we realized that the values were good enough uh, in terms of the values, or the predicted results match up the patterns and the peaks of the real consumption, or the real bandwidth in this case, which is good enough in terms of sizing. This is the result for the outbound bandwidth. For the input bandwidth, the results were again similar. In terms of memory, the same, and for the CPU, the same. However, in the CPU, you can realize that some of the predicted values were maybe matching the patterns and the peaks. However, the median values were not that good. This is good enough for maybe on-premise components. Um, for example, a company that has its own devices. However, for cloud components, um, a person that applies these techniques, I think, should keep in mind that probably these predictions are not good enough, since in cloud environments usually the resources are shared um, between several clients. Therefore, the the performance or the efficiency that those devices have, it's crucial. However, for on-premise clients, I would say it could work fine. In our case, it worked fine. Um, Therefore, it's, even though it doesn't match with the minimum values, it's good enough. Um, these are the results for the firewall. Again, the same technique, the results for every single algorithm. Um, you can see here that in the memory's case, the values were not, some of them even were negative. However, when this was plotted for the CPU, first of all, it was quite good. Nothing to say here. However, for the memory value, some of the values, according to the R square technique, uh, some of them were not good enough. However, when you plot, these values are close enough to be taken into account. That's something that engineers in this field should keep in mind. That even though the R square results um, don't match exactly, the if the plotted value match, it's good enough. Okay. Um, Something to make clear here is, for example, once you obtain your your model and is predicting really good the components, what you could do, for example, for predicting or for sizing future components, is maybe once you obtain your model, you could set or try your model by changing these values, the independent variables. For example, if in this case you had to train your model based on these values, and maybe you will increase the amount of workers of your company um, by 50 or 100 users. You have to, of course, add those users here and obtain your new values, your new dependent variables. In that way, you can size your your network or your company. The other advantage was for predicting future behaviors of for networking companies, and this means knowing how your network um, will perform in the future, or what its behavior will be like in the future. And this is really good for flood attacks and DOS or DDoS attacks. And of course, this is from a security perspective. The relationship, you can uh, you can see um, deeper the relationship that we use in the paper, but to put it simple, it was this. Um, Also, another thing to keep in mind that in this particular case, artificial neural network work better than the other models, and this is the topology that we use. You can go deeper about this in the paper again, and these were the results. You can see here that all the results, again, the results uh, were set and were also proven by using R square. You can see that results were good enough, particularly for artificial networks. The results were amazingly good. In fact, these values were something that we were not expecting. However, were good, and we are going deeper, in fact, with our research about this. Anyway, the plotted behaviors, you can see them here. You can see that the expected behavior, these are behaviors that we predicted with machine learning, and this is the real behavior. Of course, as you can see, the values match quite good, and yeah, well, that is an indication that we could use this practically we could use this practically in every uh, network device to perform or to enhance the security of those devices. Um, as conclusions, well, the useful uses of machine learning data networks have been presented. The results were good enough to demonstrate that machine learning is a good advantage that can be added to this field, whether for sizing of resources in network devices or predicting future behaviors for networking components. Machine learning works fine. Some things to keep in mind are uh, for sizing, the results don't have to be measured completely based on R-squared coefficient, yet also taking into account the plotted values is due to the correlation of real and predicted values is compared in real time. The probability of predicting every single value is low. Nevertheless, despite this fact, the patterns and peaks can be predicted really well to obtain a finite model to use it for calculating future behaviors or sorry, future resources for as many devices as we want. Also, the final results or the final models and machine learning formulas can be inserted in monitoring tools like Nagios, which was used in this paper, or a new platform that can be even created by ourselves. Examples, some apps, for example. Uh, for prediction of networks behaviors, the current paper was also looking for reducing security gaps, and amazing results were found. Artificial networks have demonstrated to be the best model to predict future behaviors in data networks. This is showing us that we could actually know how our network could be in the future in terms not just of traffic, how it was demonstrated here, but also about more values that are not being approached here yet, that we could easily extrapolate. In fact, as next step, new applications on predicting protocols, connections, sessions will be addressed, as well as looking for uncertainties, prediction models in monitoring systems and networking devices to add them a higher rate of intelligence and act immediately under every scenario that doesn't comply with the normal behaviors and predictions. Um, these are the main references that we use for papers, and that would be all. Thank you so much for your attention and have a good day.